Okay. So we have just started with the free fall, but as I said, I'm not going to solve too many problems. So the free fall motion is going to be important. We are going to revisit this later, right? In many different contexts. So as a result, I'm not going to, I'm kind of justified in not solving many problems. All right, but let's just remember this, right? That's what I have said last time. All objects in free fall have the same acceleration. So the magnitude of the acceleration is shown by letter G, all right? We just call this as gravity. And it's directed towards the center of the Earth. All right, so there's some kind of annotation in here. When I use this scalar quantity G, right, it's just the magnitude of the gravitational acceleration. So for Earth, of course, this is equal to 9.8 meters per second squared for Earth. For the surface of the Earth, sorry about that. For the surface of the Earth. It's a positive quantity because I define it as the magnitude, right? It is never negative. So when I write G, you always should understand that that's the positive number in there, right? I never place a minus sign. The minus signs have some other meanings, right? But I'm also going to use this vector G for denoting the gravitational acceleration. So it's basically the vector having that magnitude and directed towards, directed downwards, right? So I'm just going to use this notation, and sometimes I'm going to use that notation, right? But I will basically explain the meaning of these notations later, right? In any case, so as a result, when I say gravity, I might mean the vector quantity or the scalar magnitude, right? So there's some kind of an ambiguity in the usage of this one, but I don't think that that's too important. Let's remember what free fall is, right? It's the motion only under the effect of the gravitational pull of whatever. So that means the object doesn't need to be falling. It might also be rising, or I don't know, it might be moving or like that, or doing projectile motion, for example. So all is included, all right? So in the use of scientific terms, we just look at the precise definition. Okay, so in solving these problems, I'm just going to do it like that. So that's the ground in here. So we are going to throw objects up and I don't know, and then we are going to look at their motion, for example. When investigating the motion of these objects, I can choose my x-axis to be pointing up or down. So some people just call this as the y-axis. So I can also name this as the y-axis as well. So since in the three-dimensional kinematics, I'm going to call this as the y-axis, I'm just going to make this choice in here, right? So as a result, there are these different choices in here, right? I can call the name of the axis in a different way. I can choose the upward direction as my positive direction, or the downward direction as the possible direction. So let's say it like this. There are many possible choices. Okay. So for this choice, for example, if the y-axis is pointing upward, since the gravity is downward, we will say that the acceleration, the y component of the, well, acceleration is equal to the gravity. So we know this. So as a result, in this reference frame, the y component of the acceleration is minus g, okay? So that's a negative number in that case. The y component of the gravity or the y component of the acceleration is a negative number in here. Or I can choose the y-axis to be pointing downward. Gravity is still the same, right? The physics doesn't change. The acceleration of the objects are still the same, but the y component of the acceleration is now plus gravity, okay? So as a result, the difference between them is just the, I mean, since when you're using the scalar quantities for expressing the accelerations, you may want to choose the acceleration as a negative quantity or positive quantity, but that depends on how you have chosen the reference frame. Okay, that's the important point in here. And for that reason, for the next problem, I'm going to solve the same problem by using these two approaches again. We will get the same equation again in both cases, but it's important to see how the equation is formed. Okay. So again, I mean, if there are any questions, please stop me. So I'm just going to go to the next question in here. So, all right. I mean, this is one of the classical questions that I always solve. So as a result, I'm going to do that in here too. So probably this also has a solution in one of these previous videos. But I'm just going to illustrate a few points in here. So a rock is thrown up with a speed of 5 meters per second. So let me say this is 5 meters per second. Yeah. From the top of a building, and the building is above the ground, 10 meters above the ground. And the question is, at which time does the object, does the rock fall on the ground? So we are asking for that time in here. Okay. In part B, I'm asking for the velocity of the rock when it is passing from the level it was thrown. So let me just write it down like that. So that's the velocity of the rock at that point. So let me actually do it like that. So I would like to use a consistent picture in here. So this is about part A, this is about part B. So let me erase this. So this is about part B. Part C is about the maximum height and so on. Yeah, I said etc. because I don't want to. I mean, you can actually ask too many questions about these, but more or less all of them are one of a few kinds of questions. Okay, thank you very much. So again, let's just look at some of the important things. Thank you for the answer. That's why I thanked. Okay. So yeah, let's just remember that I just take the gravity to be equal to 10 meters per second squared all the time, and also in homeworks, right? Also in homeworks too. Unless stated otherwise. I mean, if there's a clear indication that I ask you to take G to be 9.8 meters per second squared or 6 meters per second squared, if I clearly say so, then you have to take it like that. Otherwise, you just can assume that this is the case, all right? There's also confusion about these kind of things in the previous homework. Some people just suppose that it should be taken as 9.8. No, we just take it like that. So the important point in here is, I mean, we are learning how to use these formulas, right? So as a result, the values of the precise values of the numbers are not important. We are not engineers. We are not designing anything. We're just solving some problems and trying to see if it physically makes sense or not. Okay. So let me say this. So start with A. So that's the important part. All right. Less than, start with this. The very first step, the first step is the choice of the reference frame. Okay. I can choose the reference frame like that, where the y-axis is pointing upward. And well, I can choose the reference frame like this. Yeah, let me use a yellow color for this one. So that's the yellow solution, sorry. Where the y-axis is pointing downward. okay, where the origin is in both cases is here at the level where the rock is thrown, right? Okay, so I'm going to first solve with this and then solve with that, right? So, but let's just look at the initial values in here. So there's an initial velocity. There's a final position, right? So there's sorry about that. So there's an initial position, sorry, y0, right? And then there's a final position in here. Let's see. Yeah, let's just give all the values. So in here, the initial velocity is plus 5 meters per second. Initial position is 0. Acceleration is equal to minus gravity, so therefore it is minus 10 meters per second squared. And there's a condition in here for the solution. So I have given one quantity, which is basically the final position in here. So that's basically the ground position. So at which time the y coordinate becomes equal to the position of the ground. So since that distance is 10 meters, so that corresponds to minus 10 meters in here, right? Let me quickly do what happens if we are using this reference frame. So in that case, the velocity is negative. It is opposite to it's along the negative y-axis. Initial position is the same. Acceleration is this time is plus g. So therefore, this is plus 10 meters per second squared. And the final position, so that's our condition, is equal to plus 10 meters, right? I mean, all of these are vector quantities. Obviously, if I change the direction of the axis, all the y components change sign, okay? So that's basically something that's kind of obvious. In any case, so I'm just going to use this equation. So that's the first equation, basically, that we have written yesterday. So the position given as a function of time. So that's V0 times t plus 1/2 of acceleration times t squared. Okay. So when I write this equation like that, I mean, for the choice where the y-axis is upward, I always write down the last term like that. A lot of people just write it in the other way. So they just write it like minus 1/2 of gt squared. I suggest that you don't do this because, I mean, let's say it like this. This is the proper way of actually doing it. You first choose the reference frame, and then after that, you decide on the sign of the acceleration, right? But the formula is still the same. So all of these signs are positive in here. Okay, just keep this in mind. It appears that most of the time, when people are solving these kind of problems, they always choose the y-axis to be upward. So in that case, this can be justified. But I ask you to be a little bit open-minded. So as a result, it might still be possible for you to choose the y-axis to be downward. In some cases, this might be a little bit better point of view than the other one. And so as a result, for these kind of things, I mean, do not memorize the formula that you would use for one reference frame, right? Just memorize a formula that's valid for all the reference frames and then apply it to that one. Okay, that's basically what I wanted to say. So in any case, so we get like minus 10 is equal to 0 plus 5t minus 5t squared, right? That's the equation. Or if I just collect everything on one side, I get t squared minus t minus 2 is equal to 0. So that's the equation. Or I can, if I do the same thing with this one, I'm just going to write down the same equation. But this time, the gravity has a positive y component. So position is positive, initial position is 0, velocity is -5, and the acceleration is 5. And so as a result, you get t squared minus t minus 2 is equal to 0. Okay, so in any case, I mean, both equations are the same. So in one case, you multiply the whole equation by -1, that's it. So that also signifies that this is actually a vector equation, so all terms are vectors. So we are essentially writing down the components of these vectors along some chosen reference frame, right? That's it basically. So the next step is to actually solve this problem. I know that most of you actually do this in ÖSS style. You just look at the equation and see what the solutions are. Yeah, you can do that, no problem with this. But let me just write down the formal way of solving this. So if I have an equation like this, yeah, let me just write it down like that. ax squared plus bx plus c equals 0. Then there are these two solutions in here. And somehow I have memorized this and in secondary school, and I cannot forget it somehow. So whenever I want to write down the solutions, I just recite the formulas, minus b plus minus square root of something, whatever. It's always the symbols have the same name too. But in any case, there might be some other practical ways of actually writing down the same solution. In any case, for this case, therefore, there are two solutions of that one. So we get +1 in here, plus minus square root of 1 squared minus 4 times 1 times -2. Divided by 2a, all right, so therefore this is 1 plus minus the square root of 9. All right, so I'm just going to write down the solutions like that. Let me write it down like this, right? So we have these two solutions, t1, which is minus 1 seconds. And there's a second solution, t2, that's 2 seconds. Okay, and at this stage, we then inspect these solutions and see which one is the one that we want. So basically, the motion starts at time t equals 0. So if the rock falls to the ground, it falls at a positive time greater than 0. So therefore, the second one is the solution then, right? So therefore, the answer is plus 2 seconds then. Okay. I don't know if you have any questions in here. Let me also explain the same thing in here on the position versus time graph. So the position versus time graph looks like that, basically. So it's a parabola. In any case, it's a parabola like that, but the motion starts from here. So that's t equals 0. And the motion ends in here where the time is t equals t2. So that's 2 seconds. But of course, this is a parabola. So as an ideal shape, I can extend this graph in here. Even though the rock doesn't follow this path, I can still extend this graph in here. So it appears that this T1 in here corresponds to the time in here where, I mean, if I assume that the rock was not thrown at the initial time, the rock was continuing its motion. Somehow it was a ghost rock that can pass through the inside of the buildings and things like that, but it was always in free fall. So at time t equals 0, it was passing from the top of the building. So that's the top of the building in here. So that means that rock basically passes the ground level at 2 times. One is at time -1 seconds. So that's -1 seconds. And the other one at 2 seconds, all right? So as a result, the other solution therefore has this kind of a meaning. But of course, we know that our rock doesn't do this. It's not a ghost rock. So if you just look at the motion of our rock, it's going to be something like that. Before it is thrown, it was at rest at the top of the building. When it is thrown, it does this free fall. And at some point it hits on the ground, and then it probably jumps, and finally it just becomes at rest. So as a result, it's not a constant acceleration motion if you look at it. So only that part can be thought as the constant acceleration motion, or whatever the some other parts as well. Does that -1 mean anything? So it's -1. Yeah, it's before the time, before t equals 0. All right, so the time also continues from negative times. It becomes 0 when the rock was passing through the level of the roof. And then, yeah, whatever. Okay. So the next thing is, if negative time exists, time is measured, right? We have a clock in here, right? We have a chronometer for, let's say we have a clock, not a chronometer, right? Let's say that right at the 12 o'clock, this is thrown. And so you just look at the thing that shows the seconds, right? So you just interpret these positions as positive and the previous positions as negative, right? It's something that you read on the clock, right? So it's negative before. I mean, on one side, the time should be negative. On the other side, it should be positive, all right? That's essentially what I mean. It's basically like the coordinate, right? Like the position of an object. If it is on the right of on this side, then the position is positive. And if it is on the left side, now we don't actually express this with a positive number because we can confuse it with these ones. So as a result, we just represent them by negative numbers, right? This is always the convention, right? Just like the position when we are measuring angles or when we are measuring time and whatever. On the other side of 0, all quantities will become negative, right? That's the only meaning, right? This is something that we parameterize basically. And so as a result, we distinguish these two different sides of some origin. Okay, part B. Part B is, so part B is the question of like this one, sorry. When the rock is passing through the same level, what's the velocity? I have answered that question before, so I'm going to look at this from another point of view, all right? So part B, what's the velocity? Let's say velocity when, there's the condition in here, when the final position is equal to the initial position, which is 0. Okay, so that's the question. So let's say it like this: on position versus time graph. Okay. So we have a situation like that in here. So it's the same graph. So this is a parabola. Right? I mean, it's just this shape, right? Well, since the acceleration is negative in here, it is downward looking. Yeah, I don't know what to call this thing. So it basically curves down. That's the term in here. So in any case, if we just consider the shape, then of course this extends to infinity. Okay, so there is this one center, some symmetry axis in here. So let's say it like this, right? I'm just going to write it down like that. So parabola has reflection symmetry across this line. Okay, So as a result, if I have a point in here, right? Exactly this, and if that distance is, let's say, x, or I don't know, if that distance is x, let's say, then at that distance x, I mean, these two distances are the same, all right? So as a result, I mean, there's this symmetry in here, which means that this slope is the same as that slope. I mean, the angles are the same. So as a result, that angle is the same as that angle. But the slope in here, slope of that curve is positive and the slope of that curve is negative. So there's only a change in sign. So as a result, what I'm going to say in here is that the slope in here, whatever it is, let's just call it as V0. In that case, the slope for this curve should have the same magnitude, but should have the opposite sign. All right, so therefore, this basically tells me that if the object is passing this from the same point at a second time, in that case, its velocity becomes the negative of the initial velocity. All right, so therefore, the velocity is equal to minus V0. And so I don't know which, yeah, we are using the upward axis, right? So V0 was plus 5 meters per second. So that means the final velocity is minus 5 meters per second. Or you may want to say 5 meters per second downward if you don't want to use any axes. Usually, if the problem doesn't give you any axis to use, then normally you should also express the answer without using any axis. But in any case, I mean, let's not get too strict here. Equal to initial velocity with negative side. It's equal to opposite of the initial velocity, right? It's not. It's equal to the negative of the initial velocity. Equal to minus initial velocity. We can use, yeah, we can use the conservation of energy. And yeah, there are these other things as well. I mean, yesterday I have talked about this thing too. You can use this one, the average velocity, which is V plus V0 over 2. Or you can use this rule, which is the same thing as the conservation of energy. This is the conservation of energy statement, basically, but it appears in a different way, right? Okay, so the last one, maximum height. So it is this one. Again, so basically we would like to find, yeah, let me say it like this, all right? In this problem, we would like to find that distance, which is essentially the displacement, that distance at the time when the velocity becomes 0. That's basically the question in here, because the maximum height corresponds to the turning point. So at the turning points, the velocity becomes 0, right? So this is our condition. By imposing this condition, we would like to find the value of that quantity. Do not switch the reference frames in the middle of the problem. Don't do this, right? That's so you'll get confused, right? But there are some other things. Sometimes I'm going to, for example, if there are like many objects in the system, like 2 blocks, for example, I can choose different reference frames when I'm investigating the motion of these 2 blocks, right? So for each block, I can choose a different reference frame. So that's allowed. But for the same object, if you choose one reference frame and then another one, unless you are very clear about it, this is kind of confusing, right? But there are some questions like, for example, in relativity, we would like to look at the same physics by using these two reference frames at the same time. So there are some reasons why you may want to use two different reference frames for the same problem. But usually, if you're not doing this on purpose, then it's going to be a confusing thing. Okay, so as a result, try to avoid if you're not doing anything like that. Okay, so maximum height. All right. So in any case, I just solved this problem with this, right? V squared minus V0 squared, that's equal to 2 times the acceleration times delta y, right? That's the way to solve this, because you know the acceleration that's given, you know the final velocity, and you would like to find this one. And without computing the time to reach to the topmost point, you can solve the problem like that, right? So in that case, this is 0. The acceleration is minus g, and well, delta y is positive in here, so the right-hand side is negative. Similarly, the left-hand side, so therefore delta y is equal to v0 squared over 2g. Okay, so in this case, this is 5 squared divided by 2 times 10. 25 divided by 20, so that's 1.25 meters. So that's the displacement. If you want the position from the above the ground, you can then add 10 meters to that, all right? So I'm not going to do this. Okay. Warnings. Do not memorize, because a lot of people think that, well, this looks like a nice formula. So if there's a maximum height question, then I can just insert this thing and write this formula and then insert everything in. I suggest that you don't do this, right? The reason is that there will be too many formulas to memorize, right? The best thing that you should do is to memorize these 4 formulas only that we have written down at the beginning of the kinematics. So there are these constant acceleration formulas. Just try to keep them in mind. And I mean, there might be some certain ways that you can remember them, some easier way to remember them. So by using these, you can easily deduce these, no problem with that. So as a result, do not memorize any formula that you can easily deduce, right? It's not a difficult thing. You just need to write down one line of equation in here, and then perhaps at most in 2 lines, you can get the result, right? Just keep this in mind. Okay.
John?
Yeah.
This problem can still be solved with the other equation, right?
Yeah. With
that contains time.
Yes. So as a result, you need to solve it in 2 steps, right? So other methods. Okay. So you basically need to use this thing and somehow obtain some information and find delta y, right? That's the thing. So as a result, you can do it like that. So for example, v0 plus acceleration times t, for example. So final velocity is 0, initial velocity is 5, so that's minus 10t. So from here, you find t to be 0.5 seconds. And then after that, you just write delta y, that's v0t plus 1/2 of minus g times t squared. So that's 5 times 0.5. And then this is minus 5 times 0.5 squared, all right? So you just compute this, right? It is 1.20. I mean, it should be 1.25 meters. So that's one way, all right? You can also do it like that. How else you can do it? You also know the average velocity, but you don't know the time. yeah, I don't know. I mean, there might be some other methods as well. So once you find the time, then you can use any other method. Yeah, you can use this one. So you know the average velocity. So that's V0 plus V divided by 2. So this is 5. Final velocity is 0. So 5 over 2 is the average velocity. So delta Y is V bar times T. So 2.5 multiplied with 0.5. So meters, right? In any case, yeah, I don't know. I mean, there are lots of things that you can do, but what I'm trying to say is that, I mean, in these kind of other methods, then there are these extra things that you need to compute. Okay, so I think I'm done with the free fall motion. So we will continue, of course. So in the next topic, so let's start with the kinematics in 3 dimension. Okay, so first I'll give a general description of what's the position, what's the displacement, right? The usual kinds of things. And then I'm going to, yeah, I'm just going to do that. And after that, I'm just going to write down the constant acceleration formulas, which will be the same as the previous formulas. But this time, it will be apparent that they are vector relationships. All right, so I think this point of view will be a little bit more important, right? Let me quickly do this. The things that we have done before. I don't know how to call these, right? There's an x-axis, a y-axis, and a z-axis. So that's a reference frame. This must be chosen, usually. For expressing the positions, of course, we should also do this. So we have a particle in here. We express the position as the vector drawn from origin to the location of the particle. All right, let's just remember this position. For some reason, for some historical reason, we just usually denote the position with the letter R. But the components are just called X, Y, and Z instead of Rx, Ry, and Rc, right? Why do we call this as R? So I think it has something to do with the radial distance. So the magnitude of this thing is essentially the radial distance. But that's something else. So when we start using that coordinate, we can perhaps talk about this again, right? That's the position. And then we have the motion of the object. So the object moves, perhaps in a complicated manner, to some other position. So then we have a change in position. So I think I'm going to undo this and then draw somewhere else. So we have the object in here. So that's an initial location and that's a final location, but the object might have moved in a complicated manner to that final location. We don't care. We just define the initial position in here. That's Ri. And we define the final position, Rf. And the displacement is basically just change in the position. So therefore, it's the final position minus the initial position. All right, we have the usual difference definition in here. So you can think of it as an algebraic way of looking at this, but we also have the geometric way of understanding what displacement is. It's basically is the vector drawn from the initial location to the final location. Okay, so we know that this algebraic operation corresponds to this geometrical quantity. So I think what's important in here is that the displacement doesn't depend on the origin, where you choose the origin. Why is this important? No, I don't think that that's important. So forget what I have said, all right? So in any case, I mean, we then define the displacement like that, and all the other quantities will be defined in a similar way. Okay, so let's have a break here. Let me stop. So in the second hour, I'll just describe the velocity and acceleration, and then go ahead with the rest.